Good morning, ladies and gentlemen, boys and girls, friends and neighbors. In this video, we're going to talk about exponential functions, and not only talk about exponential functions, we're going to graph some exponential functions. They're very important in our mathematics studies in pre-calculus and calculus. We've done a lot with the laws of exponents down the road, but we've yet to look at an exponential function. Well, an exponential function is a function where the variable is the exponent. There are different forms of the exponential function that we will discuss throughout this video and the videos to come. So here's form number one on exponential function. So I have f of x is equal to c a to the x. C is just going to be a real number. C is a real number. Well, in this case, because there's a couple cases, we're going to make sure that c is greater than 0. And we're going to make sure that a is greater than 0 as well. So we don't want a to equal 1 either, because then that would just be a constant function. So we have c, a to the x. X is the variable. Take note of the variable x. That is in the exponent. The variable is the exponent in the rule of the function. The a in the definition is called the base of the function. And here's two important topics about exponential functions in this form. If a is greater than 1, then the graph is going to increase very quickly. I'm sure that you've heard somewhere in your study saying, hey, that grows exponentially. We will examine that down the road, what exponential growth is indeed. And then if a is between 0 and 1, then the graph of the function is going to decrease very quickly. Okay? So for this particular form, c a to the x, where c is greater than 0 and a is greater than 1, the domain is going to be all real numbers. Well, in fact, the domain is going to be all real numbers for all exponential functions. And the range, important to note, is greater than 0. The range is greater than 0. For this function, c a to the x, there are no x-intercepts. And the y-intercept is going to be 0, c. And this is easy to verify. What is 0? What is f of 0? F of 0 is going to be c a to the 0 power. And we know that anything to the 0 power is 1. So c times 1 is c. And that's how we get the y-intercept is 0c. It's going to be important to note in the next lesson that exponential functions are one-to-one functions. We may or may not have talked about one-to-one functions, but we will a lot next year. So let's just jump into our first example of exponential functions and how to graph them. Okay, so our first function is going to be 3 times 2 to the x. Here, the c is 3, and the a is 2. And what I'm going to do, just as we did when we were graphing radical functions, I'm going to come up with a series of points. So I'm just going to put some x values in and see what the outputs would be. So if x is negative 3, what do we have? We're going to have 3 times 2 to the negative 3. Well, 2 to the negative 3 is going to be 1/8 times 3. That's going to be 3/8. But enter just for so that we can graph it easy, and you can verify this in your calculator. That's going to be 0.375. And that is indeed 3/8. So if we put negative 2 in, what do we have? We have 3 times 2 to the negative 2. 2 to the negative 2 is 1/4 times 3 is going to be 3/4. And again, we're going to write this in decimal form because it's going to make it easier for us to graph that point. If I put -1 into the graph, and I think you know where we're going, put -1 in, we're going to get 3 times 2 to the -1. 2 to the -1 is 1/2. 3 times 1/2 is 1.5. And we've already evaluated it at 0, but we'll put 0 in for it again. If I put 0, looks like I'm going to get 3 times 2 to the 0. 2 to the 0 is 1. 3 times 1 is 3. Keep in mind this row here are my y's. I have my x's and my y's. And then if x is equal to 1, looks like it's going to be 3 times 2 to the 1. Oh, and that's going to be 3 times 2 is 6. Let's do a couple more values. Let's put 2 in for x. Looks like we're going to have 3 times 2 squared. 2 squared is 4, times 3 is 12. That's the output. And we're going to do one more rascal. If I put 3 in, looks like I'm going to get 3 times 2 cubed. 2 cubed is 8, times 3 is 24. So that's a table of values. Now I'm going to graph those points. And I'm certainly going to have to scale my x's as we've done before. My x's I can scale easily. I'm going to scale them in ones. But I'm going to have to scale my y's a little bit different. And it looks like my y scale goes all the way up, right? My outputs for 3 go all the way up to 24. So I think I'm going to do 2's. Let's see what 2's would do if I scale it. For the assignment, I'm going to ask you just to get some graph paper, and you're going to scale it yourself. You're going to draw the grid and scale it yourself. So you'll have to be familiar with how to scale. And let's just try 2's here. 2, 4, 6, 8, 10. 12, 14, 16, 18, 20. Oh, it looks like 24 is way up there. Well, that's okay. We'll just make sure he's up there. So now let's plot these points. We have -3, 0.375. All I know is that, I'm going to graph the points in blue, is that's a small number, smaller than 1/2. So that's going to be probably down about right in here. And then I have -2 3/4 about right there. -1 is about 1.5, would be about right there. At 0, it's going to be 2, so you notice we're in scales of 2 here. At 1, it jumps up to 6. And at 2, it jumps up to 12. 2, 4, 6, 8, 10, 12. And at 3, it really jumps up there. And so this is our first exponential curve that we're going to look at here. And you can see this thing does increase, and it does increase fast. This thing does increase quickly. I mean, that thing's going off to infinity really quick. So that's the graph of your first exponential function. And down the road, maybe this year, but I know in next year, we will determine why the range. This function never will get below, this particular function never will get below the x-axis. So we say the range here is y is going to be greater than 0. And the domain, of course, is all real numbers. I can put anything in. Okay, so that's our first example. Oh, let's go to example number 2. Okay, example number 2. Looks like I have 5 is going to be the C, positive number, and A is this 1/3. And keep in mind what we said. If a was between 0 and 1, it's going to decrease slowly. Well, let's find out by just creating a table of values. I have the table of values. I'm just going to fill them in. I would ask that you just make sure that the values are correct, because you're eventually going to have to do this on your own with your calculator. Where am I getting these? I am getting these, putting 0 in for x. Those are all 5s there. If I put 3 in, it's going to be 0.18519. Oh, so I'm really going to have to scale this thing crazy this time, because it looks like I start at 135. So if we did 20s, scale of 20 might be able to do it. Let's do 20s. 20, 40, 60, 80, 100. 20, 40, 60. Because if we start at -3, it looks like we're almost to 140. We're at 135, so we're way up here. We're right way up here. And then -2, it's at 45. Right here somewhere. -1, it's 15. At 0, it's 5. At 1, it's smaller yet, smaller yet, smaller yet. So that thing did decrease very quickly, almost to the point of flattening out here when it reaches the x-axis. And we'll talk about what that means when the graph flattens out down the road. We don't talk about it this year, we certainly will talk about it next year. And again, if it's exponential, the domain is all real numbers. We'll get that thing out of there. I don't know how we got there. And the range is y is greater than 0. So the only thing that changed between this example and the previous one was this decreases, and it decreases because of this a 1/3. So if you have an exponential function where the leading coefficient IC is greater than 0 and a is between 0 and 1, the thing is going to decrease. And then if your a is positive and your base is was greater than 1, then it's going to increase. So there's a couple good examples of some exponential functions. Let's see what's next on the agenda. I'm going to dock it here. So a very interesting and important property of all exponential functions, and we're going to talk about this property right here. If I have n an integer, and I take the quotient of f of n plus 1 divided by f of n, that's always going to be the base. Just look at the previous example. Well, we'll look at this example right here. Example 3, consider the function 1/2 times 4 to the x power. We're going to find f of 2, f of 3, and then keep in mind, what is f of 2? plus 1. F of 2 plus 1 is f of 3 divided by f of 2. So let's find out what f of 2 is for this particular function. F of 2 is 1/2 times 4 squared. That's going to be 8. 4 squared is 16, divided by 2 is 8. And we're going to find f of 3. F of 3 is going to be 1/2 times 4 cubed. And we notice that 4 cubed, 64 divided by 2 is 32. Oh, so f of 3, which is 32, divided by f of 2, which is 8, that does indeed equal 4. And check this out, ladies and gentlemen. That was the base of our exponent, of our exponential equation. And that works every single time. That's a very good property. We will use that property down the road to come up with the rule for an exponential function given a table of values. So very important property. Let's try example 4 on this guy. Let's see here. Let's find f of 2 again. I have a new function. This time the base a is equal to 1/4. We want to see if this is going to work. This property right here. Let's see if this property works. All right. So let's go f of, let's not use yellow. F of 2. It's going to be 5 times 1/4 squared. That's going to be 1/16. And that's going to be 5/16. We're just going to leave him right like that for right now because I think I can. F of 3 is going to be 5 times 1/4 cubed. 4 cubed is 64, so that's going to be 5 over 64. Oh, maybe it will work this time. I don't know. So what's f of 2 plus 1 is going to be f of 3 divided by f of 2. F of 3 is 5/64 divided by 5/16. And somewhere down the line, we know how to divide fractions. We multiply by reciprocals. So this is going to be the same as 5/64 times 16 over 5. The 5's cancel. And what is 16 divided by 64? Does indeed equal 1/4, which is our base this time. Okay, very good. All right, so that's going to be our first lesson about graphing exponential functions. I'm going to give you a couple problems to work on. And we'll talk about a couple more forms of the exponential function as we go. So key here, let me zoom out here and get a good picture of what we're doing. Sorry, to our page. So we looked at this exponential, we graphed it, we came up with the table of values. We noticed that C was 5, A was 1/3. Since A was 1/3, it's going to be decreasing quickly, as it did. We named the domain, we named the range. And then the first example we had, C was 3, A was 2. So it increased quickly. We did indeed name the domain, and we named the range. So that's going to be video number 1 on graphing exponentials.